Good day, everybody. How are you all? Today, we are going to construct a confidence interval for the population standard deviation. A sample of size 101 from a normal population has a sample standard deviation S is equal to 40. Construct a 95% confidence interval for population standard deviation sigma. Use table to determine the critical chi-square values. So, first is degrees of freedom. In this case, is sample size minus 1 is 101 minus 1 is equal to 100. So my C level, confidence level is equal to 0.95. Alpha is equal to level of significance is equal to 1 minus C is 1 minus 0.95 is equal to 0.05. Okay. So the first thing we need to find out is alpha by 2 is 0.05 divided by 2 is 0.025. And also we need to calculate 1 minus alpha by 2, which is 1 minus 0.025, which is 0.975. Why do we need these two values? Because if you look at the chi-square distribution, okay, so this is chi-square on the horizontal axis. It is distributed, it's a right skewed distribution. It starts from chi-square 0 and extends on the positive side to positive infinity on the right. Okay, so since our level of significance is alpha, we divide the curve, this part as area alpha by 2, and this part is also area alpha by 2. In the center, we have the confidence level, C is equal to 0.95. So the confidence interval is in the center, whereas on the two tails, we have areas of alpha by 2, where we do not want the population standard deviation to fall. We want the population standard deviation to fall in the center region, which is not shaded. So this chi-square is represented as chi-square. The area to the right of it is 1 minus area in the left tail, 1 minus alpha by 2. So it is chi-square 0.975. That is this particular alpha, chi-square. And what about this chi-square? This chi-square is chi-squared, and area to the right of it is 0.025. So each chi-square is indicated by the area to the right of it under the curve. So this one, area to the right of it is chi-square 0.975. The reason is from total area of 1, you subtract the area of the left tail, which is alpha by 2, which is 1 minus 0.025, which is 0.975. Similarly, on the right tail, the area in the right tail is alpha by 2. So you want to find out chi-squares alpha by 2. So these two are the critical values. Critical values. This one and this one. These are the critical values. How do I find the critical values? So as I said, we have to refer to the table. Okay, so let me show you the table. Remember, my degrees of freedom is n minus 1, 101 minus 1 is 100. So let's go to the chi-square table, which you can find on the web as I found on the web. So I will share it with you in a minute. Where is my chi-square table? I don't see it. Okay. So let me go to the table. Let me draw how the table looks for you. So let me go to the table and share with you. Okay. So if I may move this, so I will use the key to move it upstairs. So there's a table available on the web. Oops. Which is given by the name of the table is critical values of chi-square. Critical values of chi-square. If you search in Google with this search phrase, critical values of chi-square, you will get the table. So the table in the first column is degrees of freedom. And our specific degrees of freedom, so the first column is 100. So we are stuck with this row, which is a degrees of freedom 100. And then we are looking for chi-square 0.975 is the chi-square 975. So let me erase that and write it clearly. So on the top row, you are looking for the first, you are looking for chi-square 0.975. 975. So let me look up the table and get back to you in a minute. So if I go, okay. So with 100 degrees of freedom and 0.975, the critical value. So let me be, maybe I'll be able to share this with you. Let me now share my screen with you. Yes. So here is the table. Okay. So look at the first column. That's the degrees of freedom. I already aligned it at the end. The last entry in the first column is 100. That is what we are looking for, 100 degrees of freedom. And the third column title is chi-square 0.975. So in the third column, we are going to draw a vertical line through the third column, which is a title on the top chi-square 0.975, and a horizontal line through degrees of freedom 100, and they intersect at 74.222. So if I go back, okay, if I go back to my stop share. If I go back, my, okay, so 100, and I draw a vertical line through 0.975. This one will be chi-square 0.975. And farther on the right in the first row, I'm looking for the top title as 0.025, chi-square 0.025. And look at the intersection of that with the row 100. So this will be chi-square 0.025. So I have to write those two values from the intersection of a horizontal line through 100 and then vertical line through chi-square 0.975 equal to, and then chi-square vertical line through 0.025. So let me go back to the table again. Again, they disappeared, so I'll go back to the table in a minute. Okay. So 100 and 0.975 intersection is 74.222, and intersection of degrees of freedom 100 and chi-square 0.025. 0.025 is the third column from the right, and its intersection is 129.561. Okay, so again, I will show you the table again one more time. So this is the table, and I type chi-square table in Google, and it gave me this table from University of Arizona. Okay, so I looked at the intersection of the last row 100 with the third column 74.222. This is chi-square 0.975, and I also looked at the intersection of a horizontal line through 100 and a vertical line through the third column from the right, and it's 129.561. So going back to my screen. Okay, so let me move this up a little bit. So the critical two values are chi-square 0.025 is 129.561, and chi-square 0.975 is 74.22. So these are the two critical values. Remember, these are the critical values of chi-square. So my formula, so for confidence interval for the variance, interval for the variance, is given as n minus 1 times s square, which is sample variance, divided by chi-square 0.025 less than sigma square. Sigma square is the population variance, less than n minus 1 times s square by chi-square 0.975. So remember, let's take a look at our sample standard deviation. I believe it was 40, okay, and sample size is 100. So if I plug in the values, n is 100, 1, sample size is 101 minus 1 times s is 40 square divided by chi-square 0.025 is 129.561 less than sigma square less than 101 minus 1 40 square divided by critical value of 74.22. So 74.22. Oops, let me change the color of the ink back to what I was using before. So get rid of this and go to this ink and then write it over here, 74 point, let me make sure I'm writing the correct value, 74.22. 74.22. Remember, sigma square is population variance. Sigma square is to be read as sigma square. This is Greek small s. Sigma is equal to Greek small s. All Greek letters indicate population characteristic. Okay, so this is 100 multiplied by 40 square divided by 129.561 less than sigma square less than 100 times 40 square divided by 74.22. So let's crank out the number using our calculator. So I'll first multiply 100, then multiply it by 40, square it by pressing the x square button, divided by 129.561. And that will be 1234.94 less than sigma square less than, again, 100 times 40 square divided by 74.22, and that will be 2155.75. Now this gives us the 95, but we are interested to find 95% confidence interval for sigma, not sigma square. So what do I do? Well, we'll have to just take the square root. So this will be square root 1234.94 square root of sigma square less than square root of 2155.75. So let's take the square root of, so we do second button, then x squared, which is in the first column, left-hand column, second button and x squared, this is TI-84, gives me the square root. Inside the square root, type 1234.94 and you get 35.14 less than square root of sigma square is sigma, which is the standard deviation. Sorry, we will clarify it. Okay. So, okay, less than second x square again gives me the square root 2155.75, and this is 46.43. So if I move this a little bit up, I can write what is the interpretation of this interval with 95% confidence. We can state that the actual population standard deviation will fall, deviation will fall between 35.14 and 46.43. Notice in this case, our sample size is 101 and our degrees of freedom is 101 minus 1, which is 100. This is a large degree of freedom. Can we approximate the chi-square distribution in this case by a standard normal curve? That's a good question to ask because we know as the degrees of freedom increase, chi-square loses its skewness in the right tail and approaches a symmetric distribution. So the problem I'm going to solve next in my next video is, can we get a similar result for the 95% confidence interval for sigma using normal approximation for chi-square, since our degrees of freedom is 100, which is quite high. And as the degrees of freedom we know increase, then chi-square approach a normal distribution. So please do not forget to watch me next time, okay? When I'll come back to construct this interval using a normal distribution. So I'll construct a 95% confidence interval for the standard deviation using a normal distribution, okay? And if you like this video, please give me a thumbs up. I really appreciate that. If you like this video, share with your friends. You and your friends, please come back next time when I will construct 95% confidence interval using for standard deviation using normal approximation to chi-square distribution. Okay, so do not forget to check me out. Also, please check out my channel because I have solved all kinds of math problems just for you. My goal is to, for you to become the best in math. So please subscribe to my channel by hitting the red subscribe button at the bottom right corner. And I will see you next time. Do not forget to watch me next time. Thanks. Take care. Have a nice day.